So in this module, we continue with the filters. So we have this sine wave source Vi of t, and we have a resistor R. And instead of a capacitor, let's put a coil here. So that's an inductor. And then the loop current is indicated by I of t right over here. So we try to obtain the frequency response of this circuit. And what we note here, we write the loop equation, which is Vi of t that equals I of t into R plus j omega L into I of t. So current into resistance and current into impedance or reactance of the inductor, right? So here XL is nothing but impedance or reactance of the inductor. Okay, and with this we can write Vi of t, that is I of t can be taken out, and here we have R plus j omega L. So omega is the frequency, L is the value of inductor, and that's how we write this equation. So let's call this is equation number 1, and we develop the voltage across the inductor, that is, let's say, VO of t. All right. So VO of t would be indicated by, of course, the current flowing through the inductor multiplied by the impedance that it offers. And with this, we can write I of t that equals VO of t divided by j omega L. So that's how we get this equation. Let's number this as equation 2. And we just put the value of current, that is equation number 2, into equation 1 to get this value. We can write here Vi of t that equals VO of t divided by j omega L and bracket R plus j omega L. So as we can see, we have this, and with this we can get the gain of the circuit, which is the ratio of in output voltage divided by input voltage. Okay, so that comes out to be j omega L divided by R plus j omega L. Okay, and this can be written as 1 over 1 plus R divided by j omega L. All right. So once we have this equation, we can try to get the magnitude. So which will be written as VO of t divided by Vi of t. And that comes out to be 1 over whole square. All right. So what is to be noted here, this R over L is nothing but omega L. Okay. So that is the cutoff frequency or a break frequency of this filtering function. All right. And this 1 over omega L, which is nothing but the tau L, which is the time constant. Okay, and tau L would be L over R. So with this, and similarly, we can have the phase of this gain, which is VO of t divided by Vi of t, and that can be written as, we are writing this equation by looking at this one. Okay, so this is how we are trying to get this equation. So coming back to this, and we write here minus tan inverse R divided by j omega L, which can further be written as tan inverse omega L divided by omega. All right. So we have, let's say this is equation number A and equation number B. Okay. Because these two equations are equations for magnitude and equation for phase. So with this, we can always draw the characteristics. So first case for omega is equal to 0. That is the case number 1. We see that this magnitude equation, we put the value of omega is 0 here. So what we have, the output is 0 basically. That equals to 0. And we can try to draw this plot over here. So we see that, and that's the plot for these, for the, okay. So here omega is equal to 0. This is the plot for the magnitude. Let's call it as a gain, okay. And this is the plot for the phase. All right. So we see that this is at omega is equal to 0. We have magnitude to be 0. Okay. And similarly, let's see what is the phase. Phase would be again, it would be tan inverse infinity. So phase would be 90 degree. Okay, because we plug in the values over here. So let's say we have this value over here. This would be 90 degree. Okay, and this plot is 0. So for the second case, if we take a look at this, for omega is equal to omega L, which is at the break frequency. So in that case, you have the value of magnitude that can be seen over here. We are referring to this equation. Okay, so this factor becomes 1, so 1 by root 2. So that comes out to be 0.707. All right, and the angle would be, let's see what it goes. So it would be tan inverse of 1 with this equation. So tan inverse of 1 will be 45 degree. All right, so we come back to this 1 and we see that at somewhere here, omega is equal to omega L, right? Similarly for the phase, and this is for the gain. So your gain increases and it takes the value of about 0.707, all right? And the phase comes out to be somewhere here is about, we have to write this equation. So here it's 45 degree. And that's how it comes out to be like this. It is decreasing. Okay. And similarly, we can go for the third case, or omega tends to infinity when omega is equal to infinity. So we can write here that value. So the gain becomes 1. Why? Because omega, we plug in the value of infinity. in this equation. So this factor omega L by infinity comes out to be 0, and the output becomes 1 unity. So that's how we have this value. Okay, and this angle would become 0. All right, because tan inverse 0 would be 0. And how to draw this? We can come back here and we see that this factor becoming 1. So this gain is 1, and here omega goes to infinity, and this is how we are approaching 0 here. All right, so this is the ideal situation of this filter, and it forms the function of a high pass filter. So we see that up to omega equals to omega L, and the gain is below 1, and it approaches 0 when frequency approaches 0, and thereafter for omega greater than omega L equal to or greater than omega L, this gain becomes 1 unity, and the phase response is also can be seen from this plot. All right, so this is how we can obtain the frequency response of this filter, and we'll see another circuitry where how we can give. For instance, if we have the circuit like instead of resistor, we have a coil put in here, and we have a resistor right over here, and again we excite this with these with this input voltage source Vi of t, and we measure the voltage across this resistor which is out of. So we need to know what is the frequency response of this circuit, right? So we'll see that again in the next module.